The main electrical difference between an inverter system and a UPS system lies in how they manage power. An inverter system converts direct current battery power into alternating current power to supply critical loads during a power outage. A UPS system maintains a constant alternating current power supply to critical loads by switching between normal utility power and battery power during power outages. An automatic transfer switch manages the transfer of power between normal power and backup power sources, such as a generator or inverter. Some inverter systems have a built-in automatic transfer switch that allows them to automatically switch between normal power and battery power without the need for an external automatic transfer switch. There are advantages to having an automatic transfer switch upstream of an inverter system with a built-in automatic transfer switch. Firstly, there is redundancy. This provides an additional layer of protection by having two separate automatic transfer switch systems. Secondly, load balancing. If the inverter system has multiple inverters, the external automatic transfer switch can distribute the load evenly among them. Finally, there is flexibility. The external automatic transfer switch allows for future expansion or changes to the power system configuration. When considering emergency power systems, understanding the nuances of inverter systems, UPS systems, and automatic transfer switches is crucial for ensuring reliable power to critical loads. Inverter systems are primarily designed to convert direct current power from batteries into alternating current power suitable for powering various devices and equipment. They are commonly used in applications where direct current power source, such as a battery bank, needs to be converted into alternating current power for use by alternating current power loads. UPS systems, on the other hand, are designed to provide an uninterruptible power supply to critical loads. They typically operate by continuously monitoring the incoming utility power and, in the event of a power outage or voltage fluctuation, seamlessly switching to battery power to maintain a constant alternating current power supply to the connected loads. The key difference lies in their primary function. Inverter systems focus on converting direct current to alternating current, while UPS systems focus on maintaining a continuous alternating current power supply. Now, let's delve into the role of automatic transfer switches in emergency power systems. An automatic transfer switch is a critical component that automatically transfers power between a normal power source, such as the utility grid, and a backup power source, such as a generator or inverter system. In the event of a power outage or voltage irregularity, the automatic transfer switch quickly and seamlessly switches to the backup power source to ensure an uninterrupted power supply to critical loads. This automatic switching action is essential for maintaining the operation of essential equipment and systems during power disruptions. Some inverter systems come equipped with a built-in automatic transfer switch, which eliminates the need for a separate external automatic transfer switch. These integrated systems offer a compact and convenient solution for applications where space is limited or where a simplified installation is desired. However, there are also scenarios where using an external automatic transfer switch in conjunction with an inverter system that already has a built-in automatic transfer switch can provide additional benefits. One of the primary advantages of having an automatic transfer switch upstream of an inverter system with a built-in automatic transfer switch is redundancy. By having two separate automatic transfer switch systems, you create an additional layer of protection against power disruptions. If one automatic transfer switch fails, the other can still provide the necessary power transfer functionality, ensuring continuous power to critical loads. Another advantage is load balancing. In inverter systems with multiple inverters, an external automatic transfer switch can distribute the load evenly among the inverters. This helps to prevent overloading any single inverter and ensures that the load is shared efficiently across the entire system. This load balancing capability can extend the lifespan of the inverters and improve the overall reliability of the system. Furthermore, an external automatic transfer switch offers increased flexibility for future expansion or changes to the power system configuration. If you anticipate adding more loads or modifying the power system in the future, an external automatic transfer switch provides the necessary flexibility to accommodate these changes without requiring significant modifications to the existing system. In summary, While inverter systems and UPS systems both play important roles in emergency power systems, they serve different primary functions. Inverter systems convert direct current to alternating current, while UPS systems maintain a continuous alternating current power supply. Automatic transfer switches are essential for automatically transferring power between normal and backup power sources, and using an external automatic transfer switch in conjunction with an inverter system that already has a built-in automatic transfer switch can provide redundancy, load balancing, and increased flexibility. Now let's consider different types of inverters. There are primarily three types of inverters available, namely square wave inverters, modified sine wave inverters, and pure sine wave inverters. Each type offers unique characteristics and is suitable for different applications. A square wave inverter is the simplest type of inverter, producing a square wave output waveform. While it is the most affordable option, it is not suitable for powering sensitive electronic devices. A modified sine wave inverter generates a waveform that approximates a sine wave. It is a more refined option than a square wave inverter and can power a wider range of devices. However, it may still cause interference or damage to some sensitive electronics. A pure sine wave inverter produces a smooth, clean sine wave output waveform that is identical to the power supplied by the utility grid. It is the most sophisticated type of inverter and is capable of powering virtually any electronic device without causing interference or damage. Now, let's examine the features of an automatic transfer switch. Automatic transfer switches are available with a range of features and options to suit different application requirements. Some common features include automatic and manual operation, adjustable voltage and frequency settings, and monitoring and diagnostic capabilities. Automatic operation allows the automatic transfer switch to automatically transfer power between the normal and backup power sources without manual intervention. Manual operation provides the ability to manually transfer power between the sources, which can be useful for maintenance or troubleshooting purposes. Adjustable voltage and frequency settings allow the automatic transfer switch to be configured to match the specific voltage and frequency requirements of the connected equipment. Monitoring and diagnostic capabilities provide real-time information about the status of the power system, which can help to identify and resolve potential issues before they cause a disruption. When selecting an automatic transfer switch, it is essential to consider the specific requirements of the application, including the voltage, current, and frequency of the connected equipment, as well as the desired level of automation and monitoring. It is also important to choose an automatic transfer switch that is compatible with the inverter system or generator that it will be used with. Now let's discuss about the proper sizing of the inverter and the load. To properly size an inverter for a specific load, it is essential to consider the total power requirements of all the devices and equipment that will be powered by the inverter. This includes not only the continuous power consumption of each device, but also any surge power requirements that may occur during startup or operation. Inverter sizing is crucial for ensuring reliable operation and preventing damage to the inverter or the connected equipment. Selecting an undersized inverter can lead to overloading, which can cause the inverter to shut down or even fail. Conversely, selecting an oversized inverter can result in unnecessary expense and reduced efficiency. To determine the appropriate inverter size, it is necessary to calculate the total continuous power consumption of all the devices and equipment that will be powered by the inverter. This can be done by adding up the wattage ratings of each device. It is also important to consider any surge power requirements that may occur during startup or operation. Some devices, such as motors and compressors, may require significantly more power during startup than they do during normal operation. The surge power requirement must be taken into account when sizing the inverter. A general rule of thumb is to select an inverter with a continuous power rating that is at least 25% higher than the total continuous power consumption of all the connected devices. This provides a safety margin to accommodate any unexpected power surges or fluctuations. For devices with significant surge power requirements, it may be necessary to select an inverter with a higher surge power rating. It is also important to consider the efficiency of the inverter when sizing it. Inverters are not 100% efficient, and some power is lost during the conversion process. This means that the inverter must be able to supply more power than is actually required by the connected devices. The efficiency of the inverter is typically specified by the manufacturer. Now let's consider the design of a UPS system. A UPS system is typically designed with several key components, including a rectifier, a battery, an inverter, and a transfer switch. The rectifier converts alternating current power from the utility grid into direct current power to charge the battery. The battery stores energy for use during power outages. The inverter converts direct current power from the battery into alternating current power to supply the connected load. The transfer switch automatically switches between the utility power and the battery power in the event of a power outage. The design of a UPS system can vary depending on the application and the desired level of reliability. Some UPS systems are designed to provide backup power for only a few minutes, while others are designed to provide backup power for several hours. The size of the battery is a key factor in determining the runtime of the UPS system. The design of the transfer switch is also important for ensuring seamless switching between the utility power and the battery power. The transfer switch must be able to switch quickly and reliably to prevent any interruption of power to the connected loads. There are three main types of UPS systems, namely standby UPS systems, line interactive UPS systems, and online UPS systems. A standby UPS system is the simplest type of UPS system. In normal operation, the connected loads are powered directly by the utility power. In the event of a power outage, the transfer switch switches to the battery power, and the inverter converts the direct current power from the battery into alternating current power to supply the connected loads. A line interactive UPS system is similar to a standby UPS system, but it also includes a voltage regulator that can compensate for voltage fluctuations in the utility power. This helps to protect the connected loads from voltage surges and sags. An online UPS system is the most sophisticated type of UPS system. In normal operation, the connected loads are always powered by the inverter. The utility power is used to charge the battery, and the inverter converts the direct current power from the battery into alternating current power to supply the connected loads. In the event of a power outage, there is no interruption of power to the connected loads because they are already being powered by the inverter. This makes online UPS systems the most reliable type of UPS system. Now let's consider the common maintenance needs of the UPS system. UPS systems require regular maintenance to ensure reliable operation. Some common maintenance tasks include battery testing, battery replacement, and system cleaning. Batteries are a critical component of a UPS system, and they must be tested regularly to ensure that they are able to provide the required backup power. Batteries typically have a lifespan of 3 to 5 years, and they must be replaced when they reach the end of their lifespan. System cleaning is also important for preventing dust and dirt from accumulating inside the UPS system. Dust and dirt can cause overheating and other problems. It is important to follow the manufacturer's recommendations for maintenance. Regular maintenance can help to extend the lifespan of the UPS system and ensure that it is able to provide reliable backup power when needed. Now let's discuss the importance of grounding. Grounding is an essential safety measure for all electrical systems, including inverter systems, UPS systems, and automatic transfer switches. Grounding provides a low impedance path for fault current to flow back to the source, which helps to protect people and equipment from electrical shock and fire hazards. Proper grounding is required by electrical codes and standards such as the National Electrical Code, also known as NEC. The National Electrical Code specifies the requirements for grounding electrical systems. The size of the grounding conductor must be sized according to the size of the circuit conductors. The grounding conductor must be connected to a grounding electrode, such as a ground rod or a metal water pipe. It is important to ensure that all electrical equipment is properly grounded to prevent electrical shock and fire hazards. Now let's discuss the different types of automatic transfer switches. There are primarily two types of automatic transfer switches, namely open transition automatic transfer switches and closed transition automatic transfer switches. An open transition automatic transfer switch momentarily interrupts power to the connected loads during the transfer process. This is because the automatic transfer switch must break the connection with the normal power source before making the connection with the backup power source. A closed transition automatic transfer switch, on the other hand, does not interrupt power to the connected loads during the transfer process. This is because the automatic transfer switch makes the connection with the backup power source before breaking the connection with the normal power source. Closed transition automatic transfer switches are typically more expensive than open transition automatic transfer switches, but they provide a more seamless transfer of power. The choice between an open transition automatic transfer switch and a closed transition automatic transfer switch depends on the sensitivity of the connected loads to power interruptions. For critical loads that cannot tolerate any interruption of power, a closed transition automatic transfer switch is the preferred choice. For less critical loads, an open transition automatic transfer switch may be sufficient. Now let's consider the standards, compliance, and regulations in the area of Missouri. Electrical installations, including those involving inverter systems, UPS systems, and automatic transfer switches, are subject to various standards, compliance requirements, and regulations. These requirements are designed to ensure the safety and reliability of electrical systems and to protect people and property from electrical hazards. Electrical codes, such as the National Electrical Code, provide detailed requirements for the installation, wiring, and grounding of electrical systems. These codes are typically adopted and enforced by local jurisdictions. In addition to electrical codes, there may be other regulations and standards that apply to specific types of electrical equipment or installations. For example, there may be regulations governing the installation of emergency power systems in hospitals or other critical facilities. It is important to consult with a qualified electrical contractor or engineer to ensure that all applicable standards, compliance requirements, and regulations are met. Failure to comply with these requirements can result in fines, penalties, and even legal action. Now let's review the use of different electrical components. In electrical systems involving inverter systems, UPS systems, and automatic transfer switches, various electrical components are used to ensure proper operation and safety. Some common electrical components include circuit breakers, fuses, surge protectors, and voltage regulators. Circuit breakers and fuses are used to protect electrical circuits from overcurrents. They are designed to trip or blow when the current exceeds a certain level, interrupting the flow of electricity and preventing damage to the equipment. Surge protectors are used to protect electrical equipment from voltage surges. They are designed to divert excess voltage away from the equipment, preventing damage from lightning strikes or other voltage transients. Voltage regulators are used to maintain a stable voltage supply to electrical equipment. They are designed to compensate for voltage fluctuations in the power grid, ensuring that the equipment receives a consistent voltage. When selecting electrical components for an electrical system, it is important to consider the specific requirements of the application. The components must be rated for the appropriate voltage and current levels, and they must be compatible with the other components in the system. It is also important to choose high-quality components from reputable manufacturers to ensure reliability and longevity. Now let's review different factors to consider during installation. The installation of inverter systems, UPS systems, and automatic transfer switches requires careful planning and execution to ensure proper operation and safety. Some important factors to consider during installation include location, ventilation, wiring, and grounding. The location of the equipment should be carefully selected to ensure that it is protected from the elements and that it is easily accessible for maintenance. Ventilation is important for preventing overheating. The equipment should be installed in a well-ventilated area to allow for proper air circulation. Wiring must be done in accordance with electrical codes and standards. The wires must be sized appropriately for the current that they will be carrying, and they must be properly insulated. Grounding is essential for safety. The equipment must be properly grounded to provide a low impedance path for fault current to flow back to the source. It is important to consult with a qualified electrical contractor or engineer to ensure that the installation is done properly. Improper installation can lead to equipment damage, electrical shock, and fire hazards. Now let's consider the advantages of using a generator system for backup. Generator systems are commonly used as backup power sources in conjunction with inverter systems and automatic transfer switches. Generator systems provide a reliable source of power during extended power outages. They are typically powered by diesel, natural gas, or propane. Generator systems can be sized to meet the power requirements of a wide range of applications, from small homes to large industrial facilities. When selecting a generator system, it is important to consider the power requirements of the application, the type of fuel that will be used, and the noise level of the generator. It is also important to ensure that the generator system is properly installed and maintained. Regular maintenance is essential for ensuring that the generator system is able to provide reliable backup power when needed. Now let's consider the cost involved. The cost of inverter systems, UPS systems, and automatic transfer switches can vary depending on the size, features, and quality of the equipment. In general, larger systems with more features will cost more than smaller systems with fewer features. The cost of the equipment is just one factor to consider. There are also installation costs, maintenance costs, and operating costs. Installation costs can vary depending on the complexity of the installation. Maintenance costs include the cost of regular maintenance and repairs. Operating costs include the cost of electricity to power the equipment and the cost of fuel for generator systems. It is important to consider all of these costs when evaluating the overall cost-effectiveness of different power solutions. It is also important to consider the potential cost of downtime. Downtime can result in lost productivity, lost revenue, and damage to equipment. A reliable power solution can help to minimize the risk of downtime. Finally, if working on any electrical device, make sure to always use a calibrated meter and wear all appropriate PPE.